This is part 2 of 3 of the lecture on the properties of the Z transform. So again, here there's a typo, so I fixed it.
In this second part, I will focus on two properties of the Z transform, which are time reversal and conjugation. The fourth property is time reversal. By time reversal, we mean that by flipping the signal about the origin. So, for example, so if I have, let's take this signal here. So let's suppose x of n is a right-sided signal, a n mu n. So it looks something like this. If this is 0, it decreases exponentially. Then the time reversal is x minus n. So it's going to be the symmetric over 0. So what was 1, it's going to become -1, and so on and so forth. So if this is xn, this is this is n, and xn is here, and this is x minus n. So this is going to be equal to an u minus n, or a minus n, u minus n. And in this case, you can see that if we find the Z transform x minus n here, so the Z transform is going to be equal to the sum from n equal to minus infinity to 0, a minus n z to the power minus n, right? So and what I can do is here's the, and what I can do is I can do a change of variable. So we can take let's call m equal to minus n. So this is going to be equal to the sum from m equal to 0 to plus infinity am zm, right? So this is going to equal to the sum from m equal to 0 to plus infinity am so here I can say that this is so I can write this as z to the power minus 1 to the minus m. So, and as you can see, so this is exactly x of z, but instead of z, I have z minus 1. So this is xz to the power minus 1. Right, so because x of z is equal to the sum of from n equal to 0 to infinity of an z minus n, right? So the connection between x of z and the reverse time version of x is that you replace in the z transform, you replace z by z minus 1. And here I just did an example. It's easy to see in general. It applies in general. So this is basically the formula that we have. All you have to do when you have time reversal is once you do a time reversal, you just replace z by z minus 1. Now the question is, what is the ROC here? Again, we can test it against the example we have. So let me do it in different color here. So for x of n, so again, I'm gonna keep working with the same example. So for x of n, here for x of n, we have x of z, and the ROC is z, the norm of z greater than a, because it's a right-sided signal. Now for x minus n, the z transform of it, we know that it's xz minus 1. And when does this converge? Again, it's the same kind of principle, so let me highlight it here. So this function is going to converge x of something if this something is satisfy this condition here. So whatever inside must satisfy this condition. And this means that what I get in the end is the following. So the ROC is going to be equal here to the amplitude of z minus 1 greater than a. Because whatever the argument of the function is, must be the norm of it must be greater than a. And this will give you that z is greater than 1 over a. So as a summary, if you have time reversal, then you can obtain the z transform by replacing z by z inverse, or z to the power minus 1 in the z transform. And for the ROC, you're gonna replace also z by 1 over z. And let me explain this more on the next slide. So like we just saw, this is the formula that gives you the time reversal property. And here we say that the ROC is maybe in a, to represent it in an easy way, we say that the ROC of the time reverse signal is 1 over the ROC of the original signal. What does that mean though? So this means that if Z0 is in the ROC of x of n, then 1 over Z0 must be in the ROC of x minus n. In some sense, you just, in the equation of the ROC, you just replace z by 1 over z. That's what it's saying. So if you have a left-sided sequence, it's going to become right-sided. So if you have the ROC is double-sided, so the norm of z is between a and b, then with the ROC of the time reverse signal, the norm of z is going to be equal to between 1 over b and 1 over a. So let me maybe give an example here, quick example. So let's suppose your ROC is this. For the signal, the ROC of x of z is this. Let's suppose it's a double-sided signal. So it's the ring between, let's say, 2 and 3. Then the ROC of x of z minus 1 will be the ring between 1/3 and 1/2. Yeah, sorry here about the circle, but I guess the main thing is that let me write them down. So here I have 1/3 and 1/2 and 1/3, whereas here I have 2 and 3. So again, this is maybe a compact way to describe what's happening, but what does that mean? It means that in the equation of the ROC, just replace z by z minus 1. Property 5 concerns conjugation. And to remind you, the conjugate of a complex number z, so let's suppose z in Cartesian coordinates can be written as a plus jb, where j squared is equal to -1. Then the conjugate of this number would be a minus jb. Or if z is in polar coordinate is rej theta, then z star would be equal to re minus j theta. So you're just basically taking the reflection of it, or the symmetric point of it, across from the real axis. So for instance, if I have z is here, then the star, or z star would be here. And you can see in polar coordinate, it has, z star has the same amplitude as z, but the angle is a negative angle, so this is negative theta. So the question here is, what is the z transform of the conjugate of the signal? So the signal x star of n, and the property tells you that the z transform of the conjugate of the signal is the conjugate of the z transform evaluated at z star. So you have here It may be a little bit confusing, but you have to replace z by z conjugate and then take again the conjugate of the whole function. To show you why this is true, let me take an example, a small example. So let's suppose we have the following signal. So x is equal to j delta 5, let's suppose. So it's just a single pulse x of n. Sorry, delta n minus 5 here. So let me draw it again. I'll write it again. So let's suppose x at 5, I have a pulse of complex. The value of the signal is complex, and it's equal to j. And then, so this can be written as x of n equal to j delta n minus 5. Then x of z is going to be equal to j z minus 5, right? That's just by applying the definition. And of course, the ROC is everything here. ROC is the whole complex plane. The only problematic case here is the origin because you have a negative power of z. Now, if we let's take y of n to be x star of n. What does that mean? It means that you take at each time n, the value of y is equal to the value to the conjugate of the value of x. So this means that x star y of n is minus j delta n minus 5 because you just take the conjugate of the values. Now, if you do y of z here by just applying the formula, so you're gonna get minus j uh, z to the power minus 5. And now, if you look at the formula, what does the formula say? So the formula says, let's take x star of z, right? So what does x star of z? X star of z is gonna be jz minus 5 star, the conjugate of all these terms. So it's gonna be the star of j, the conjugate of j, which is minus j, and the conjugate of z to the power minus 5, which is z star to the power minus 5. And now you see that when you take the conjugate of x, you don't really get y of z. You get minus j, which is, this is the correct term, so you have minus j here and minus j. But you also did the conjugate of z, which is z star, whereas here, z remains z. So that's why you have to do the conjugate again. And now, so if we try to evaluate this, so let's try to evaluate what would x star of z star be. So this would be minus j. So instead of z, we replace it by z star. So this is going to be z star to the power minus 5. And we know that the conjugate of the conjugate is the number itself. So this is going to be equal to minus g z to the power minus 5, which is actually equal to y of z. And this is actually what's happening. And again, the ROC is the same. So again, so it may be a little confusing that, well, I have to take the conjugate. So the z transform of the conjugate of the signal is not equal to the conjugate of the z transform. It's equal to the conjugate of the z transform evaluated at z star. And here, through this example, what I was hoping is that to convey to you why you need to do this. Because if you take the conjugate, you're going to take the conjugate of the signal, the constant here, which is the right thing to do, but also you're going to take the conjugate of z, and this is why you have to kind of calibrate that. So you have to bring it back to z from z star. So this is why you evaluate it at z star, so z star star equal to z. And the ROC remains the same. So let's try to understand more some properties of conjugation. So if x of z has a polar 0 at z equal to z0, then x star of z star must also have a pole at the complex conjugate point, which is z equal to z star 0. So again, if x of z has a pole at z equal to z0, then the conjugate x star of z star has a pole at 0 star. Let us take an example. So let's suppose that x of z is equal to z divided by z minus j by 2. Then x star of z, so I'm taking the conjugate of everything, so it's going to be z divided by z minus j by 2, which is star, which is equal to z star divided by z star plus j by 2. And now if I do x star z star, I flip back the z star to z, so z divided by z plus j by 2. So you can see with the x star z star is flipping the coefficients and the constant and keeping z z. And now you can see here that in the original function here, in the original z transform, so z equal to j by 2 is a pole, whereas here you can see that z equal to minus j by 2 is a pole. So this is to say again that if z0 is a pole of x of z, then z0 star is a pole of x star z star. Now, if the signal x of n is real, then you know that its conjugate is going to be the same. So x of n and x star of n is the same, which means that the z transform of the conjugate is going to be the same as the z transform of x of z. So x star of z star is equal to x of z. So what does that imply in terms of properties of x of z? This is what I want to talk about now. So basically, we know that if x of z has a pole, let's suppose at a pole at z0, pole at z0, I'm going to take z0 equal, like I did in the previous example, equal to j by 2. And x of n is real, then this cannot happen. Why is that? Because what you need to have also, so because we know that if x of z has a pole at g by 2, then x star of z star has a pole at negative j by 2. But we know if xn is real, then x star z star is equal to x of z. This means that x of z must have a pole at j by 2 and a pole at z0 equal and a pole at its conjugate z0 star equal minus j by 2. So this is why for when the signal is real and whenever you have a complex pole, you must have another pole which is its conjugate. So x of z here, if x of n is real, then x of z should always have the pole and its conjugate. So it must have z minus j by 2 times z plus j by 2. So that's what this property is saying, and this is it's a good property to know and to check your results against, because most of the signals at least we're going to work on and we're going to use in this class are going to be real signals. So in the case when you have complex poles, you must have also the conjugate of these poles. And here I have an example to highlight this fact. So I'm not going to do it in detail, so I'm just going to leave it to you to check out the definitions and the calculations. But the question is to find the z transform of the following signal, 1/3 to the n sine pi by 4 n u of n. And my reason why I chose this example because the signal is real. So here, that's the main thing to notice here. So x of n is a real signal. But still we can get complex poles. So if you do it using Euler's formula, so all we need to do here to use Euler's formula and then you divide sine, and then you have these two parts, and then you apply the formula we know, and you get the nice expression of the z transform. And you can see here that you have minus 1/3 ej pi by 4 and minus 1/3 e minus j pi by 4. So you can see that both these numbers, if you have, this is the pole, these are conjugates, conjugate poles. And this makes sense because x of n is real. So this is just an example. I didn't want to do it in detail, but you should do it in detail. But this is to highlight to you how you can start from a signal that is a real signal and get complex poles, and for each complex pole, its conjugate must also be there. And as a goodbye gift at the end of this lecture, I have a small exercise for you to try it yourself, is to find the inverse transform of the following signal, and it's a left-sided signal. So find the inverse z transform of x of z equal to z cubed divided by z minus 1/2. Of course, you're going to use some of the properties we learned today, and some of also other formulas you learned in this chapter.